In this video, we just have a couple of examples of connected particles with friction involved. And if you can imagine in this question, if the coefficient of friction is 0.4, so that's telling us that this bench here is rough, and we're asked to find the acceleration of the system. And the first thing that we do is we annotate, or we draw a diagram. So I'm just going to annotate this one. And looking here, we can see that I have a weight of 12G acting down, and I'm going to have a normal reaction acting up. There's going to be a tension in the string acting away from that particle, and a tension in this string acting away from that one. And we have the weight of the 8 kilogram mass, that's 8G2. But also then we have, because this is a rough surface, we have friction involved. And I mean, I can see that the acceleration is going to go in this direction here. And I can tell that this is going to go down. Because if I do a quick calculation of mu r here, mu times the normal reaction, you'll see the normal reaction here is 12G. And if you do 12G, you get 117.6, and if we multiply that by 0.4, we get 47.04 newtons. So the maximum frictional force is going to be 47.04. 8G is going to be much more than that. So this is going to cause this to go down, and so this will go across. But let's put that into this diagram, because it's going to go, this is going to go to the left, so my friction is going to be acting backwards to the right. So we've got all our forces drawn on. Like any connected particles, then we're going to consider each mass and the forces in each mass, and then we're going to add those two equations together. But first thing first, what I want to do is find out what R is. So I'm going to resolve up and down here on the 12 kilogram mass, and it's very easy to see R is equal to 12G. Now, once we know that, what I'm going to look at is the 12 kilogram mass. And I'm going to use F equals ma on that. And you can see here that if it's going in this direction, then the overall force is T minus whatever mu r is. So it's T minus mu r is equal to the mass, which is 12, times the acceleration, so 12a. So let's keep going with that. That's T minus, well, mu is 0.4, r is, we've just worked out 12G, and that equals 12a. And so finally we get T minus, what's that, 4.8G equals to 12a. And let's call that equation 1. So if we move over to the 8 kilogram mass, let's use F equals ma on it. And this one's much more straightforward. It's much like what we've seen in all connected particles or pulleys. The force is going down, so 8G, take away the tension, is the overall force. So 8G minus T is equal to 8A. And that's the second equation. Now, if we take those two equations and as always add those two together, the tensions cancel out, and what we get is 8G minus 4.8G is equal to 8A plus 12A, so 20A. 20A equals, that works out as 31.36, and so A equals 1.568, or let's do it to three significant figures, 1.57 meters per second squared to three significant figures. In this second example, we're going to go through this in exactly the same kind of manner. Look at F equals ma in both particles and then add them together. We just need to be careful that this particle here is on a slope, is on an incline. And so again, it's going to mix our connected particles along with our inclined planes, and our friction is all going to be involved in this. But first thing first, let's draw a diagram and annotate it. So I know there's going to be a normal reaction here. I know the weight of this is going to act straight down to 5G, and the weight of this 8 kilograms is going to act down to, so 8G. I know there's a tension acting away from each body in the string. And the last thing is there's going to be an acceleration, and the heavier object is going to go down, so the 8 kilograms is going to go down. But that means that if this is travelling up the slope, then my friction has to act down. So we're going to write that as mu r. And because it's travelling, it's going to be maximum value of friction. So we can just write mu r. Last thing in there, I'm just going to put in, just to help me out here, this angle here is the same as the angle of incline. So it's the same as this angle. Now, once we've done that, let's, first of all, instead of resolving vertically to find r, this time, because it's at an angle, we need to resolve perpendicular to the slope to find r. And you'll see then that r is equal to 5g cos 45. I'm going to leave that for the minute. Now what we're going to do is we're going to look at each individual particle. So let's look at the 5 kilogram particle to start with. And as you can see here, it's moving up the slope, so it's t minus mu r. But don't forget about the component of weight. We need to resolve this down the slope. The weight will always have a component down the slope, so don't forget about it. So we see that t minus mu r minus this 5g sine 45 is equal to the mass times the acceleration, so 5a. And let's fill those wee bits and pieces in. This is t minus, well, mu in this case is 0.5. R we've worked out as 5g cos 45 minus 5g sine 45 equals 5a. Now, let's call that equation 1. Equation 2, much easier when we look at the 8 kilogram mass. And again, I should have maybe started the last one with F equals ma. But the overall force is going this way, it's going down. So it's 8g minus t. So 8g minus t is the overall force, is equal to 8a. That's our second equation. So again, let's add these two equations together. 1 plus 2 added together. The tension here cancels with this minus t. And so all that we're left with is 8g minus this a half of 5g. So that's 5 over 2g cos 45 minus 5g sine 45 is equal to, and when we add the 5a and the 8a together, we get 13a. By putting that all into our calculators, we get 26.4277 is equal to 13a. And so a equals, and it works out to be 2.03 meters per second squared. And again, that's 3 significant figures. But again, no matter whether we're talking about a flat surface or an inclined plane, we go about it in the same way. Let's find the normal reaction by resolving perpendicular to the slope. So in this case, that was at right angles to the slope, whereas in the previous one, it was just up and down, was at right angles to the slope. Then we consider F equals ma on both particles. And one of those will have positive t, one will have negative t, so that when we add these together, t's will always cancel out, and we'll be able to find the missing value.